This is a presentation on qualitative analysis of social media by AYUSH PAREEK. The basic outline is that I'm going to explain the meaning of qualitative analysis and take one of its examples, that is sentiment analysis, in detail. We are going to work with various traditional and modern methods to achieve good results on this task. Now, before we dive deep into this topic, let us discuss some basic terminology starting with qualitative data. Now, suppose that you want to know about a soccer game that you missed last week. You're given 2 points of information, the score and a complete newspaper report on what went down in the game. Now, what would a person be more interested in? The answer is that it depends. If you're a manager or a statistician, you might be more interested in just the quantitative results. But most of us don't just watch matches to know the results. It is the rich experience which is made up of a lot of unquantified information which captures our imagination. So, for example, which player was trying the hardest? What were the most crucial moments in the game? Who missed a goal by a tiny margin, and so on. So, qualitative data is subjective information about qualities which cannot be measured. Now, let us talk about the general method for analyzing qualitative data. It is divided into 3 components. The first step is to describe the data. So, taking the football match as an example, when they show post-match highlights, they are essentially describing specific portions of the match which can give you a complete picture of the entire event. The second component is classification. For instance, dividing those highlights into parts which are favorable for team A and those which are favorable for team B. This way we have started making sense of the highlights with respect to analyzing the performance of a specific team. But even that might not be enough. What if we want to understand and even predict the next entries in our data? So we need to perhaps connect these discrete data points and make sense out of it. For example, we can extract speech from this video and look for terms like swift, quick on the feet, master of the ball, etc. to find a group of players who are described as having good speed and footwork. So we have gone from plain statistics to extracting more meaningful information about the match. So qualitative analysis is the subjective judgment of unquantifiable data to extract meaningful information. Now let's take sentiment analysis as an example of qualitative analysis. So it's a process of computationally identifying and categorizing the opinions expressed in a piece of text. So how is this part of qualitative analysis? So in this example of a hotel review, we are describing important qualitative information in terms of the highlighted text. Then we classify them into positive and negative statements, and then a bunch of such hotel reviews can be connected to find the overall sentiment score towards the hotel. So sentiment analysis, of course, has vast applications ranging from politics, investment, and especially e-commerce such as fashion, electronics, automobile, etc. So we have covered the basics of qualitative analysis and sentiment analysis. Now we will discuss our research problem and find multiple methods to tackle it. Sentiment analysis is a subset of classification problems in natural language processing. Let's look at the general approaches to solve such problems. The first approach is rule-based, which means that we use an existing lexicon to find the sentiment of each word. Now, even though this approach is easy, it is not very accurate. There are nuances in language such as sarcasm which cannot be pre-recorded. Hence, we need to focus on the other 2 approaches, that is the probabilistic methods and deep learning methods, to make our prediction. Now, before we move on, we need to discuss a very fundamental term, that is feature. A feature is an individual measurable property. Choosing informative and independent features is a crucial step for classification. The most common feature set for text is n-grams. So just to explain, an n-gram is a contiguous sequence of n words taken together. So unigram would just be individual words, and bigram would be a sequence of 2 contiguous words taken together, and so on. Let's discuss some literature review. So first we have Go, Bhavani and Huang, who reported that knife base gives best results with n-grams as features. Then we have the work of Park and Parubik, who used hashtags as additional features along with n-grams, which unfortunately resulted in a decline in performance. Then
Columbus, Wilson, and Murray used a supervised approach where they prepared a lexicon which would have labels such as positive and negative attached to the word. But this approach also did not give very good results. Other researchers concluded that unigrams are better features for movie reviews, whereas bigrams and trigrams give better results on product reviews. Recently, a CNN-based model for sentence classification was proposed, which gave superior performance on text classification. Now, this literature review gives us two observations. First, there is no common consensus on whether unigrams work as better features or n-grams work as better features. So, if we can make a general corpus for testing our methods, we could find out which one is better. Also, it would be great to compare the probabilistic methods with the deep learning methods on this general corpus. These observations result in two research questions. First, which combination of features give better accuracy for sentiment analysis on a general corpus? And second, how can we optimize for accuracy on this general corpus? Now let's talk about how to make a general corpus in the first place. One of the major challenges in sentiment analysis of Twitter is the collection of a labeled dataset. We use two datasets for training and testing classifiers. The first one is Twitter Sentiment Corpus, which contains more than 5,500 tweets on 4 companies: Apple, Google, Microsoft, and Twitter, and they are classified as positive or negative. The dataset we used is the Stanford Twitter Corpus, which has more than 5,000 tweets labeled as positive or negative. The corpus was created by using various query terms on Twitter API, including movies, persons, and other miscellaneous keywords. Now, since we are using both datasets, it contains product reviews from the Twitter Sentiment Corpus and movie reviews from the Stanford Twitter Corpus, plus other categories of tweets from the miscellaneous keywords used in making the Stanford Corpus. Hence, we have formed a more generalized corpus which takes comparable amount of tweets from both the corpuses. Now, we will test different feature sets to get our results on this bigger dataset. User-generated data is not always present in a usable form for learning. Now, it becomes important to normalize this text by applying a series of pre-processing steps, otherwise the set of features would be too sparse for processing. So this tweet is a typical example. Just like in text analysis, we have stop words, we have certain Twitter-specific features which do not add any value to our analysis. Hence, it is better to remove them. For example, we find and replace several features like retweet symbol, hashtags, handle, punctuation, emoticons, etc. Observe that by removing these 7 features, we have reduced the number of words to about 53% of the original corpus. So this means that 47% of the words have been removed just by finding and removing these 7 features which specifically occur frequently in a tweet. Next, we will perform stemming, and the remaining text would be converted from its various forms of the verb to its roots. For instance, play, playing, and played would be reduced to the root play. These are the few rules of the famous portal stemmer. If we take unigrams as features, so we have generated a frequency matrix from the dataset and plotted the unigram versus frequency graph of the most common unigrams in the dataset. Now, another important point to note here is whether we should pay attention to frequency of a term or the presence of the term. So let's say that a tweet contains the word fantastic. So that means it probably is a positive tweet. But let's say that the tweet contains the word fantastic 5 times. Now this doesn't make it any more positive. Therefore, we are going to just use 1 to denote the presence of the word and 0 denoting its absence. We try n-grams as features. So even intuitively, we can understand that as we go towards higher dimensions of n-grams, the frequency of a particular pattern would reduce. So if an n-gram occurs only once, it doesn't make sense to include it in our analysis. So we only use bigrams which occur multiple times, and this graph shows the 50 most frequent bigrams that occurred in our dataset. Perform TF-IDF and feed our vectors into the naive-based classifier. So here we are trying to maximize the probability of a class given a document or a tweet in our case, and using Bayes rule we can write this expansion, and since the denominator is independent of the class, we can remove it from the argmax function. Now we can separate the documents into individual words from x1 to xn, and now by the naive Bayes assumption, the product of these individual probabilities would be equal to this value. Now substituting this into our equation, we get the argmax as this value. Now we can find the individual values of the probability of a word given a class by taking the fraction of the words count in the class upon the sum of counts of all words in that class. Now we will add 1 on both numerator and denominator for smoothing purposes, because let's say if the count becomes 0, then this whole probability would become 0, which is not desirable. The SVM implementation, the basic idea is to maximize the margins of the hyperplane that split the data points into two parts and hence act as a binary classifier. Now support vectors are these points which are nearest to the hyperplane. Now let's define our loss function and our objective function for maximizing the margins of the hyperplane. So we will use hinge loss, which is used for maximum margin classification, most notably in SVM itself. So here C is the loss function, X is the sample, Y is the true label, and Fx is the predicted label. This plus sign means that if the result is negative, then we will set it to 0. So as you can see, our objective function of the SVM consists of two terms. This first term is the regularizer, and it is the heart of SVM. The second term is the loss. So this term balances between the margin maximization and the loss. Now this lambda is a tuning knot. If it is too high, then we will overfit. If it is too low, then we will underfit. So what do we mean by optimizing our objective functions? So that means we are minimizing our loss and we are tuning our lambda to the optimal value so that we don't underfit or overfit. Look at a different approach. Instead of hand engineering features, let's use neural networks to find the optimal features and do the classification. There is a basic difference between our traditional probabilistic approach and neural networks. In the traditional approach, such as naive Bayes and SVM, we have to go through pre-processing, then extraction of features, and then using a machine learning classifier to get the predicted label. In contrast, deep learning methods can work end-to-end without any pre-processing or feature engineering steps. Before we discuss our deep learning methods, let's see if we can improve our word encoding model. So currently we are effectively vectorizing each word with a one-hot encoded vector. Now to convert a word into a vector, we find its location among all words in our vocabulary and put 1 there representing its frequency. Then we put zeros for all the other positions in the row. We can take this sum of all these word vectors to form phrase vectors. Now the problem with this approach is that there could be thousands of columns due to the volume of words in our dataset. Now these vectors are problematic for two reasons. First, they have very high dimension, which is going to take a lot of computation power to process. Second, the notion of similar vectors means vectors which share the same words rather than those which occur in the same context. For example, the cosine distance between the sentence dog sitting here and cat resting there is going to be 0 because they do not share any single word, even though they have very high contextual similarity. So let's see what we can do to change that. So in neural networks, we usually prefer dense representation, which means that we can replace each word with a dense vector which is much shorter. For example, one such pre-trained model is known as word2vec, which has about 300 columns for each word. Now word2vec has this nice property that words which occur in a similar context in terms of neighboring words tend to have vectors that roughly point in the same direction. For example, in word2vec, the highest cosine distance to the word France is actually another country, which is Spain. So now we can replace each word with a dense vector of 300 real values, and we can just take a sum of these vectors to have a low dimensional contextual representation based on word2vec embeddings. And although this could work in practice, let's see if we can improve further. For words vector space model, we experimented with different n-grams as feature vectors. The problem with that approach could be that there would be so many feature vectors and many of them would not even be useful for recognizing specific patterns. So let's try to solve that problem. To make n-grams, we will use a convolution operation with a filter of size n. So in this case, we have a filter of size 2. Now when I perform a convolution operation, which means doing element-wise dot product of these two matrices, I get a high activation, which means that this filter can recognize the phrase cat sitting. These vectors have similar values for similar context. The phrase dog resting will also give a high activation with this filter. So this means we can then capture high level features such as an animal taking a rest irrespective of the specific words which are used to describe this phenomena. So now we can extend this idea to have multiple filters of multiple lengths such that each filter tries to learn one specific feature. Slide this window over our sentence embeddings and create a feature vector of fixed length that will record the activation for a specific filter. Now this filter in red is going to slide all the way from top to bottom and record its activations in a feature vector here. But we cannot use this feature vector as our final feature into the neural network. And the reason is that it depends on the number of words in the sentence, which can vary. So we can just take the highest activation in this feature vector as a representation of the one feature that it detected with the strongest activation. In the same way, we can record the maximum values of each filter into our final feature vector, whose elements will represent the highest activation observed by each filter. So mathematically, this Ci represents a single element of this feature vector, and this is obtained by a non-linear function which takes the product of weights of the filter and the input word embeddings plus a bias. Here h represents the size of the filter, so we slide the window and obtain the feature map C. Now this operation is known as convolution. And then the highest activation of each filter gets stored in this final feature vector, which is known as pooling. This way we can make multiple layers of convolution and pooling to construct our convolution neural network. The last layer would be fully connected with a softmax function for giving the output of probabilities. For implementation, we will use the Keras library. We will first pad our review tweets in such a way that they contain 1600 characters each. Then we will use word-to-vec embeddings of length 300 to encode these sentences into word vectors. So our model is going to have 3 convolution layers of dimensions 64, 32 and 16 respectively, because that was reported as one of the better models in Kim's 2014 paper. Here we will introduce dropout, which is used to deactivate 20% of the neurons to make sure that the model doesn't overfit. Then we will have a fully connected layer with 180 neurons, and which uses 6-point function as the nonlinearity. Then again dropout to avoid overfitting, and a final fully connected layer. Then we will fit our model and find its accuracy. Experiments by taking combination of features and classifiers to determine the best classification results through traditional methods and modern methods. So we have unigrams with naive Bayes, unigrams plus bigrams with naive Bayes, unigrams plus bigrams plus trigrams with naive Bayes, and the same combination with SVM. We also have convolution neural network with 3 convolution layers and 2 fully connected layers as it was implemented in Kim's 2014 paper. So let's see what the results come out to be. The accuracy of unigrams is the lowest for both naive Bayes and SVM. The accuracy increases as we use higher order n-grams. The best probabilistic method turns out to be unigrams, bigrams and trigrams with naive Bayes. Now it's important to note that naive Bayes performs about 3 to 4% better than SVM with similar features. However, the performance of convolution neural networks is the highest, with about 2.85% margin over the best traditional probabilistic method. In conclusion, we use sentiment analysis as an example of qualitative analysis and chose certain feature sets to identify which one works the best for our dataset, and found that for a mixed dataset with movie reviews, product reviews, and other miscellaneous stuff, unigram plus bigram plus trigram on a knife based classifier gives the best accuracy with respect to traditional methods. The modern deep learning method is, however, most accurate with about 2.85% more accuracy than the best probabilistic method. So in future work, we will try to improve our sentiment analysis method by trying out more different features. In terms of deep learning, we will experiment with more architectures such as recurrent neural networks with long short-term memory cells for classification. We can also explore further methods of qualitative analysis such as text summarization and text classification. So these are the references. Thank you very much.